So this morning I'm going to be talking to you about how we use Puppet at Server Density. And we've been using it for about 2 years out of the 4 years that the company has existed. And we're using it for the standard use case. Everyone is using it for config management. But what I'm going to focus on is some of the more unusual use cases and just how we're using that to control pretty much our entire infrastructure and how we deploy our application. So my name is David Mitten, and I'm the founder of Server Density. We do server monitoring and website monitoring. We look at your website and the response times from different locations around the world, and then we get into your servers and report back stats, give you graphs, and wake you up in the middle of the night so you can fix those problems. And Server Density is deployed entirely exclusively on Linux, and we use the Ubuntu 12.04 release across around 100 servers now. And about half of those are virtualized. And we've got 2 main deployments in the US, in SoftLayer's 2 data centers. But we also have quite a large number of nodes all over the world, so we can monitor you from different locations. And the primary technology stack is built up using Nginx for our load balancers, Python for pretty much all the back-end processing, and we use MongoDB exclusively for various different use cases, from queuing to time series data to storing the data just as a standard data store. And there's a couple of legacy applications written in PHP back in the olden days when I originally wrote the application. And we're processing about 25 terabytes of data a month through the system, which isn't the massive scale, but it's pretty big, and it means we have some interesting performance challenges. Now, the primary use case that originally got set up with Puppet was for config management. And for the first couple of years, it was just me and a couple of employees, the early guys. And we got up to around 30, 40 servers without any official config management at all. And it was when we were deciding to move from our old hosting provider, Terramark, over to SoftLayer that we decided it would be a good opportunity to define all of these instances so they could be easily, or more easily, migrated to a different provider. And it was at that point that we got all the manifests set up, defined each server, and then moved it over. As our use increased of all these servers, we started to decide to use Puppet for different things. And this grew very organically, just because Puppet was there, it was at the center of our infrastructure, and it made sense to use it for a couple of things. So I'll talk for a couple of minutes about the config management, just how we do that generally, but I'm going to go into much more detail about how we use it for handling failover, so failover between individual nodes and also across data centers, and also how we use it for code deploys. And we use Puppet to deploy all of our application code, which is built up in a service-oriented architecture, so we can deploy individual components very easily. And how our entire engineering team is able to deploy things. They can run the entire environment locally, and that replicates what we have in production and just pressing a single button to deploy. And we also use it for handling system updates so that we can apply changes across groups or the entire set of servers. Because we have a relatively large number of servers, we don't want to be doing that manually. So the first way that we use Puppet is as standard as config management. And we have a single base manifest which is applied across all of our instances. And we use this based on a single repository that we have in GitHub. And this is our Puppet repository, so where all of our modules and all the code exists. And this is very, very simple. It simply gets updated on the Puppet master every 10 minutes using a cron job. It just gets pulled down, which makes it easy to commit changes in and have them appear across the infrastructure within a couple of minutes. But we can easily just log in and run a git pull if we need to update it immediately. And this base manifest exists across every single one of our nodes, and it defines some standard libraries and things that we need on every single instance, things that don't really change, like time zone settings and additional modules you might want to need in Python, but it really just defines the very base of how we deploy Puppet. And originally when migrated from the old environment to SoftLayer, it was written just as a manifest. We didn't use any of the official open source libraries or anything from the Forge or the community. It was much quicker and easier just to go through and define everything. But as we've extended our use and we're deploying new applications, so in particular, we've started to use Nginx in the last 12, 18 months or so. We've taken, instead of writing everything from scratch, we decided to use those Forge modules because it makes it a lot easier to get access to the built-in functionality. And in many cases, we've extended the Forge modules and contributed them back where the basic functionality is just not there. Now, we consider the base module to be essentially at the top, and we think about it in a hierarchy. This isn't really built into Puppet, but it's how we understand it. And underneath that, we have various sub-modules and sub-manifests, which are then applied to different groups of nodes, as you'd expect, depending on what their use case is. So, for example, we have some modules that are specific to SoftLayer, where there's a couple of quirks that we need to work around. The same on Rackspace with firewall rules and Amazon and all the different providers that we have. So you can think about this as having the base module at the very top in the architecture, and then we have a couple of different modules that go within that. And although that architecture that hierarchy doesn't exist within Puppet in a visual way or a conceptual way, it's just how we think about things. So moving on to the more interesting, unusual use cases. Perhaps the first one that we started using it for was for failover. And the way we do this is basically by defining IP addresses within the host file. And this is essentially implementing our own simple version of internal DNS. And we're not at the stage yet where we think we need to run our own DNS cluster to resolve host names. So we do this through the host file. And you can see here we've got different clusters powering the different components of server density. And we define the IP address on the top level. So that goes into the base manifest. And this then applies across every single server. And it allows us to repoint nodes very, very easily so that we can change which nodes are accepting requests. We can group it, and you can have fairly fine-grained control over which hosts receive updates and making changes and having them cascade down so that we can apply changes to groups of servers. We could conceptually do A/B testing within the environment by sending requests to different nodes. But perhaps the more interesting one is how we do load balancer management. And we use Nginx for our load balancing because it's got good WebSocket support, and through our web requests go through that. And every single cluster that we have powering all the different components has its own load balancer set up. And we define the nodes that are members of the load balancer group, the proxy group, within the specific manifest. You can see at the bottom here, perhaps, there's a couple of host names for the web servers. And we simply, within the code, iterate through those and pull them out and put them in as the members of the group. So on the Nginx level, it still manages the health of the nodes and can decide when to pull them out. But it means we can very easily remove nodes and add them back in without having to log into any servers and without having to do anything by actually getting into the server. And it means that when we're dealing with failover and on-call issues, we can just use the Puppet web UI to make changes to the whole architecture and then force the nodes to run the Puppet and the Puppet agent. And that makes it really easy for us to remove nodes from the load balancer rather than having to mess around with command line tools. And although the command line is a lot more powerful, generally speaking, when you're in a failover situation, perhaps it's going to be in the middle of the night or when you're tired, you really don't want to have to be figuring out what commands to execute. And it just streamlines that process when we're going through our checklists of things to deal with in a failover situation. Now, we also use something similar to handle failover of Puppet itself, the Puppet master. And we do this by defining the hostname Puppet and a public IP address. And all of the requests to the Puppet master hit this public IP. But this is no usual public IP, and it's a feature that we use that's provided by SoftLayer called their global IP address. And this is perhaps one of the most powerful features that they offer as a company, and not many people know about it. And it's essentially the same as an elastic IP address on Amazon, except it's not restricted to a region. You can point the IP address at any of your nodes in any data center and have it update. We've seen it pretty much instantaneously. They say there's a potential for a couple of minutes latency, but we've never seen that. And it means that we can repoint IP addresses to any node in any data center and, without impacting customers. And we do this on our front end, so we can do completely transparent failovers between data centers. But when it comes to Puppet, when you have that single Puppet muster and you need to failover, then we can do this without having to update any of the infrastructure. We can just do it on the soft layer side of things. And the IP address reroutes immediately. Now, we're currently experimenting with OpenStack, and I believe OpenStack, the networking side, has a similar feature, and you can point IP addresses all around to any node. And you could implement something similar using the Amazon Elastic IP addresses. But the key point that we get from the soft layer feature, and hopefully from OpenStack as well, is that we can point it to any IP address. And this is useful if you've got an entire region that has failed or an entire data center. And this kind of stuff is really important because you have to expect that you're going to have outages. And Puppet helps us to deal with these because it means that we can have our on-call rotation. There's 12 of us in the company. Not everyone is an operations engineer, although they are all engineers. And it means that they don't have to fully understand the entire infrastructure right down to the code level. The step-by-step things that we might need to do in a failover situation, like failing over an entire data center, can be done through a fairly easy-to-use graphical interface. And that just removes any kind of errors that are likely to happen. It just really makes it a lot simpler when you don't want to be dealing with complexity when there's a failover. And Puppet also helps us to test all our different vendors. And we do regular failovers between data centers, and within our databases, we regularly test these. But we also like to test our vendors. And this is whether you can get support from them at critical times. Is the phone number working? We had an issue with one of our vendors where their UK phone number just didn't work. And we had to use their US number instead. And these are the kind of things you don't want to be discovering when you actually need them. So regularly testing things, using Puppet to orchestrate this throughout your entire infrastructure is very, very easy to do. And it gives you a single location to do that. And you can use it to simulate failovers and essentially play war games. And this is something that we don't do currently, but it's something that we want to do in the future, is to actually copy the likes of Google and simulate an entire failover situation and have our team get paged on call and actually go through the steps of fixing problems in a simulated environment. And when you're using something like Puppet to control your entire infrastructure and to define the infrastructure, it's a lot easier to do this because you can control individual servers, you can make changes to it, those can cascade down, and it gives you that single location to be able to run these simulations. So the next use case is how we deploy code. And this is a fairly straightforward process, and it's probably something you're all familiar with if you do software development. And it starts with the commit. So the code that we commit goes into GitHub. And we use a standard method of working where the master branch is considered stable, and that's what is always deployed on production, almost always deployed on production. And any work that's happening goes into branches. And everyone's working on their own branches. Occasionally they're pulling in from master if there's new things landing, but it means that you're separating your code from production. And as soon as the commit happens, then this triggers off a build. And this goes to our BuildBot server. So we have integration tests and unit tests on a large proportion of our code. It's increasing over time as we're fixing bugs or introducing new functionality. And the commit on the master and also on all the branches triggers this build. And this goes through a number of steps. In the PHP example, there's very little to do. We use Composer to handle all the packages that we use within PHP, and within Python we use build-out. And this creates a small environment which is entirely separate from the actual global server environment, and it creates artifacts that you can then deploy. so you're not interfering with the main server system core packages. Once the build is completed, then the next step is to deploy the code. And we do this using Puppet. Every single component has an endpoint, and at each one has what we call the build version. And this version it describes what's currently on each individual node. And when we hit that deploy button, the build version is changed, and a Puppet run is then triggered. And the Puppet run notices that build version has changed, and then starts running through a number of steps. We have built a graphical interface on top of this, so we can see what version is deployed on each of the nodes, and whether how that compares to the master and the current stable version. And it's this that we use to trigger that Puppet run, so that Puppet notices that there's something different between what is actually in production and what we want to get out. What we know on the Puppet master side is the version we want to be deployed, and it differs from that version that is defined on each of the components. And these builds are controlled through a fairly basic web interface that we built, and all of our engineers have access to this. And it lists all of our repositories from GitHub. It lists the master, and it shows the latest stable build, which is at the top. And then it also goes through all of the branches. And any developer can, at any time, press the button and choose exactly which servers they want to deploy them onto. So in this case, we have our alerting set up. We've got 4 core servers as part of that cluster, which are behind a load balancer. And then we've got 2 staging servers. And you can choose to deploy it to every single one of them. If we're pushing out and we're finished with the code, we want to push it everywhere. Or we can deploy it to staging for testing, or just 1 or 2 of the production nodes if we wanted to test something. And we can do this with branches as well. And we use this primarily for deploying onto the staging environment, but every so often we want to deploy a branch onto production, perhaps to test a specific fix, or to release code in a specific order to different customers. And that button changes the build version file, and then it triggers the mcollective command to run the Puppet agent once on each of the nodes that you select. And this then triggers that Puppet agent run. It uses the build version to compare, and the Puppet run goes through and updates the code. Now, in the case of PHP, it's just a case of overwriting the file, and the web server picks it up straight away on the next request. With our Python code, there's often more in-depth steps involved, particularly with our Celery queue processing, where we've got to restart daemons. But each component has a list of steps that the Puppet agent will go through. It'll deploy the code, it'll restart daemons, it will do various things that are necessary. And all of this is integrated into our company chat room, which is HipChat. GitHub use Campfire to do this. It's a similar concept, and it allows the individual engineer who's pressed the button to see exactly what's happened. We've got the build succeeding here at the top. Then the code is being deployed. In this case, it's being deployed all of the master branches to our staging environment. And then a minute later, the Puppet run has completed, and we can see on that one particular node that the code has been deployed and which version has gone out. And this is used for the engineer who's pressed the button, so you get feedback into the chat room that everyone's logged into at any time anyway. But it also means everyone else in the company who's logged in can see what code is deployed and when, what's going on production, has a fix gone out, those kind of things. And it's about giving feedback to everyone involved, so you can see passively what's gone on, what people are working on. Now, there are a couple of advantages to using Puppet and reasons why we use it. And the first one is APIs. And you get access to all of the Puppet APIs to query that as part of the build process, so all the information that Puppet has. And perhaps the biggest one, when we were writing this, we were replacing an old build system which was hindering development. And so we wanted to get something out as quickly as possible. And because Puppet is already on every single one of our servers, it made sense to make use of it so that we didn't have to write code to iterate over SSH and try and copy files and build our own deployment system. We don't have to build daemons. We don't have to figure out how to interface with the operating system, initd scripts, for example, for restarting daemons. All of this functionality is built into Puppet. And it means that we can just leverage that without having to build any own custom code, apart from the UI that sits on the top and the integration with BuildBot. So whilst there was some development involved, a lot of the complicated stuff in terms of the operating system side of things and deploying code over many servers is already handled by Puppet and mCollective. And you get access to the system facts. And we don't do much with this currently, but it means that you can query PuppetDB or any other part of Puppet to selectively deploy code to different areas, and you can make your deploy system very, very intelligent about what it's deploying and where. But there are a few disadvantages, and the main one that we've been grappling with is that it is slow. And this is because it takes time for the Puppet agent to run. On our high-spec database servers, for example, which are dedicated servers, and then the Puppet run is very, very quick, maybe a couple of seconds. But on the nodes that we have, say in Singapore or Tokyo, these are fairly low-spec VMs because they're just doing web requests. They don't need high-spec instances. And in those cases, the Puppet agent can take time to run. And in some cases, we've seen it takes 30 or 40 seconds to do nothing, essentially, other than deploy our code. And you can also get deadlocks, because if Puppet happens to be running already as you trigger the mCollective run once, then you're going to have to wait, because the Puppet agent can only run one instance at a time. And this means that the entire model is eventually consistent. This is the way that we think about it, because when you press the deploy button, you don't get an instantaneous deploy of the code, which is the ultimate that we want to get to. Just by the nature of how Puppet works, is once you issue that mCollective command, you can't control when Puppet is going to run. You don't know when it's going to complete, and often servers will have code deployed at different times, sometimes within a couple of seconds, ideally, but sometimes it's a couple of minutes after each other. And in most cases, this isn't a problem, because our code handles this, but the one case where it could be an issue is when we're deploying the UI. Because we have a couple of servers behind a load balancer and they're round-robin distributed, it means that a customer could land on one load balancer with code at version 1, and then on the other web server, it could be at version 2, and you'll get some inconsistencies there. And we haven't solved that yet, and we're not sure whether we can solve it with Puppet. But it just means that the model you have to understand is eventually consistent. Now, system updates is the final use case, and it's very simple. It's been just built out of exactly how we want to access updates and get them deployed across the servers, and it's just a simple bash script that we run, and it uses remote commands to, as part of mCollective, to execute apt updates or whatever it is on the server. And you can see at the bottom here, it's just a simple command to the RPC aspect of Puppet to issue updates. But the main point of this is that we have defined different servers so that we can update them in different orders. So we use Landscape from Canonical, and we pay them a small amount for support mainly to get access to this, because it gives you a single location to get notifications when there are updates, in particular security updates. Those are the most important. And we have particular times of the month where we're deploying these updates across our servers. And the most important ones that we want to get out as soon as possible are the security ones. And we subscribe to mailing lists, and Ubuntu have a very good feed for this. But other packages that are not part of LTS, for example, you have to find different locations for that. And Ubuntu Landscape allows us to centralize this. But the reason we split out all the servers into different groups is so that we can use a canary concept. And this allows us to deploy code changes to very specific groups of servers. And we have a group that's representative of the entire infrastructure. And it means we can deploy updates to just a single web server and a single database server, a single queue server, and then observe that and make sure that the updates don't cause any problems. Because although we're testing against our code, there's always going to be that unusual issue that you couldn't test against, or a bug that comes up, or a regression in an update. And Puppet is a great way to very quickly destroy every single one of your instances. And we don't want to do that. So we choose to update a very specific number and observe them, run tests on them. And once we're happy, then we deploy across the rest of the server fleet. And we also use pinning of versions in a very small number of cases. Because in most options we want to get the latest version, but occasionally there's a library with a bug that we haven't got a fix for yet. But in particular with our database, we don't want that to be updating, and we don't want different versions across different clusters. And so we pin the versions here to make sure that we can control the update process and control which versions are deployed when we provision new servers. Because particularly with databases, you have to do updates in a specific order, and you don't want things happening automatically. Although we don't do automatic updates, you want to understand which version is going out. Now, as I mentioned, we're starting to experiment with OpenStack, and we're looking at moving off SoftLayer and deploying our own hardware because our use case is that servers are posting back to us all the time, and we have a very consistent traffic pattern. It's only increasing, and there are no spikes ever, apart from maybe when AWS is down and people are logging in. And so we are able to get very significant cost savings from buying our own hardware. And this is a very quick snapshot of the instances that make up what I've just been talking about, our staging environment and the Puppet Master itself. And we recently purchased a Dell server to replace these. And we're replacing 6 VMs with a single one-use server, which is significantly higher spec than all of the instances put together, and is significantly lower cost as a result of actually buying the hardware rather than renting it from SoftLayer. But because we're replacing it with a single one-use server, we understand that we're removing that level of redundancy of just being able to spin up new VMs very quickly on SoftLayer, or having multiple devices, multiple instances. They're all going to be on a single server. And so we're building this server to have internal redundancy. So we've got things like dual PSUs and dual network interfaces. And we've got hot swappable SATA drives in a RAID 10 setup. So the data center stuff can really easily pull out a disk and put in a new one without us having to go to the data center. Once we move our entire infrastructure across, then we're going to be across 2 data centers, and we're going to have multiple server redundancy. But this is for our internal tools, and having some downtime of a couple of hours if something critical goes wrong with the server, we've considered is not a critical issue currently. So just buying a single server is enough right now. Perhaps in the future we will deploy across multiple servers here, but we consider the chances of failure on a single server to be within acceptable ranges, so that we can just experiment with this single server. And the main reason that we're doing this is because dedicated and paying SoftLayer is very, very expensive. And the main reason you're paying for this is because they're keeping hardware in stock. We pay a lot of money for our database servers. So for example, an 800 gig SSD is $300 a month from SoftLayer, where we can buy the same thing for about £350. So we'll pay back that cost very, very quickly. But you are paying for the managed support and the extras that you get around going with a company who runs the data center and runs all the hardware. We very rarely have to submit tickets to SoftLayer anymore, and we can deal with everything ourselves. But when there is an issue, maybe once a month, if that, then it's because something's wrong with our infrastructure. But the reason why most people go with managed hosting providers like Rackspace or any of the others is because you get that support. And in particular, when it comes to networking, because if the network breaks, then usually it's a catastrophic issue, and you having to deal with that can be a pain. So having to have that in-house expertise is not something that every company wants to deal with. We're a tech company, so we can do that. And it means that we can get very, very high-spec servers, higher than we're currently paying for, at a relatively low cost. And the only downside is that you have to pay for the total cost of the server up front. So that one Dell server is £2,500 or thereabouts, compared to paying $450 a month. But after 8 months or so, we'll have very easily paid that back. But you do need the internal skills. You do have to have that expertise in-house to do the development and the racking of the servers and to building all that infrastructure yourself. But of course, it's a lot more fun. And building servers and playing around with hardware is good fun until you have to go to the data center. And the pricing behind this is perhaps the most complicated aspect of pre-deployment, because the way you pay for co-location running your own hardware is by paying for networking and power, and there's no real consistency in how providers charge for this. Sometimes it's in amps, sometimes it's kilowatt hours, there's carbon offset charges, there's different commit levels, there's 95th percentile billing, it's very complicated. And the only way that you can figure out what power usage your server has is by actually testing it, maxing out all the CPUs, all the disks, and plugging it into a power monitor to see how much memory, how much power is actually being drawn from there. So this is the next step of our infrastructure for running Puppet, and it's going to be an interesting experiment. The server was picked up on Friday, and it's being deployed on Wednesday. So if you're interested in reading more, I've written a lot about all the choices for the hardware and looking at all the different co-location providers in London as we're deploying to, and you can have a look on the blog. And that's it. Thank you very much.